Orthogonal vectors. First of all, definition of orthogonal vectors. Let V be an Euclidean space. V be an Euclidean space. Then, number one, two vectors alpha and beta belongs to V are said to be orthogonal vectors, said to be orthogonal vectors if inner product of alpha beta equals to 0. Orthogonal হলে কি inner product of alpha beta equals to 0 if alpha beta belongs to Euclidean space V. Now second one, a set of vectors alpha 1 alpha 2 dot alpha n in Euclidean space V called a set of orthogonal vectors if inner product of alpha I comma alpha j equals to 0 for I not equals to j. Similarly, now orthonormal vector. Orthonormal vectors. Definition. Let V be an Euclidean space. Then number one, two vectors alpha beta belongs to Euclidean space V are said to be orthonormal vectors if inner product of alpha beta equals to 0 and norm alpha equals to 1 and norm beta equals to 1. Both norm alpha and norm beta has to be 1. What is norm alpha? Norm alpha equals to the inner product of alpha alpha. Similarly, norm beta equals to the inner product of beta beta. Similarly, the second one is a set of vectors alpha 1 alpha 2 dot alpha n in Euclidean space V is called a set of orthonormal vectors if inner product of alpha I comma alpha j equals to 0 for I not equals to j and inner product of alpha I alpha j equals to 1 for I equals to j. Now primary concept. First of all, triangle inequality. Let V be an Euclidean space and alpha and beta belongs to V. Then we have to prove that norm of alpha plus beta less than equals to norm alpha plus norm beta. Proof. Here alpha and beta belongs to Euclidean space V. Therefore, alpha plus beta also belongs to Euclidean space V. Therefore, norm alpha plus beta square equals to inner product of alpha plus beta comma inner product plus alpha plus beta equals to alpha plus beta comma alpha plus inner product of alpha plus beta comma beta, that is also equals to inner product of alpha alpha plus inner product of beta alpha plus inner product of alpha beta plus inner product of beta beta, that is equals to norm alpha square plus 2 alpha beta plus norm beta square. Now for this line to this line, we know that norm alpha equals to root over inner product of alpha alpha, that is norm alpha square equals to inner product of alpha alpha, inner product of alpha alpha. Similarly for norm beta, we can say that norm beta square equals to inner product of beta beta, and by symmetric property norm beta alpha equals to norm alpha beta. So that is why we can say 2 alpha beta, 2 into inner product of alpha beta. Now for this line, it is less than equals to norm alpha square plus 2 norm alpha beta, norm beta plus beta square, norm beta square by Cauchy Schwarz inequality. We know that what is Cauchy Schwarz inequality? Modulus of inner product of alpha beta less than equals to norm alpha into norm beta. From this we can find this. So we have norm of alpha plus beta square less than equals to norm alpha square plus 2 norm alpha into norm beta plus norm beta square, that is equals to norm alpha plus norm beta whole square. Hence norm alpha plus beta less than equals to norm alpha plus norm beta. Hence proved. Now the second property. Pythagoras theorem. First of all, statement, let V be an, second concept, let V be an Euclidean space then norm alpha plus beta. We have to see that norm alpha plus beta square equals to norm alpha square plus norm beta square. We have to prove that. Proof. Here we have alpha beta belongs to Euclidean space V with inner product of alpha beta equals to 0, and alpha plus beta also belongs to Euclidean space V. Therefore norm alpha plus beta square equals to inner product of alpha plus beta comma alpha plus beta, that is equals to inner product of alpha plus beta comma alpha plus alpha plus beta comma beta, that is also equals to inner product of alpha alpha plus beta alpha, inner product of beta alpha plus inner product of alpha beta plus inner product of beta beta, that is equals to norm of alpha square plus 2 into inner product of alpha beta plus norm beta square, that is equals to norm of alpha square plus norm beta square. Hence proved. Now third concept, parallelogram law. Definition, let V be an Euclidean space and alpha beta belongs to V, then norm of alpha plus beta square, we have to prove that norm of alpha plus beta square plus norm of alpha minus beta square equals to 2 into norm alpha square plus norm beta square. Now proof. Here alpha beta belongs to Euclidean space V. Therefore alpha plus beta also belongs to Euclidean space V, and alpha minus beta belongs to Euclidean space V. Therefore norm of alpha plus beta square equals to inner product of alpha plus beta equals to alpha plus beta comma alpha plus inner product of alpha plus beta comma beta equals to. Similarly, we find this value. Now norm of alpha minus beta square equals to inner product of alpha minus beta comma alpha minus beta equals to inner product of alpha minus beta comma alpha plus inner product of alpha minus beta comma beta equals to inner product of alpha alpha plus minus beta comma alpha plus alpha minus beta plus inner product of minus beta comma minus beta, that is equals to inner product of alpha alpha minus inner product of beta alpha minus inner product of alpha beta plus inner product of beta beta equals to inner product of alpha alpha minus 2 inner product of alpha beta plus inner product of beta beta, that is equals to norm alpha square minus 2 inner product of alpha beta plus norm beta square. Thus norm of alpha plus beta square plus norm of alpha minus beta square equals to 2 into norm alpha square plus norm beta square.